Good morning, all. In this lecture, I will explain about phase space diagrams. So, what is the meaning of phase space? It is the space spanned by generalized coordinates, generalized momentum. Okay, we already have the notion of configuration space in classical mechanics. It is the space spanned by generalized coordinates. Here, this space is spanned by generalized coordinates and generalized momentum. You can draw phase space diagram only for one-dimensional problems. That is, problem having only one generalized coordinate. In that case, you can mark the generalized coordinate on the x-axis and generalized momentum on the y-axis. Okay, so the two axes, the two perpendicular axes, you can denote it on the horizontal axis. You can mark generalized coordinate, and on the vertical axis you can mark generalized momentum. Okay, so this is the phase space for one-dimensional case. If you have a system of 2 degrees of freedom, then there will be two generalized coordinates and two generalized momentum. So it is not possible to draw a 4-dimensional space. Even not imagine, it is not possible to visualize that 4-dimensional space. Okay, so only in the case of one-dimensional case or system with 1 degree of freedom, you can visualize the phase space diagrams. Okay. So that is all about phase space. It is the space spanned by generalized coordinates and generalized momentum. Configuration space means it is the space spanned by generalized coordinates. So you can even draw the configuration space for a system having 3 degrees of freedom. Okay, then in that the axis will be generalized coordinates. Okay, for example, for a system of 2 degree of freedom, the configuration space, the horizontal axis will be one of the coordinate and the vertical axis will be another one. Okay, phase space means a space spanned by generalized coordinates and momentum. Now we will discuss how can we plot the diagram in the phase space or the trajectory of particle in the phase space. Okay, so we will consider some examples. The first case is, as always, it is harmonic oscillator. As harmonic oscillator. So harmonic oscillator, we have Hamiltonian H is equal to P square by 2m plus half k x square. Here this Hamiltonian is total energy and it is a constant. Harmonic oscillator is a conservative system. Its Hamiltonian is nothing but total energy and it is a constant. Okay, so V of x, the potential energy, is half kx square. What I am going to do is, I will plot this potential energy. I will plot this potential energy. So I can plot V of x versus x, and the nature of graph will be a parabola. Half kx square, it will be a parabola. So it will be something like this. Half kx square will be a parabola, right? This is half kx square. So as x increases, the potential energy increases for both positive and negative values of x. As x increases, potential energy increases. Now, you all know that kinetic energy P square by 2m plus V of x is a constant. This P square by 2m is actually T. T plus V is equal to constant. So as x increases, V increases. This implies T should decrease. Why? because t plus v is a constant. As v increases, t should decrease. Then only its sum will be a constant. So kinetic energy will decrease. T decreases implies momentum will decrease. So in the phase space diagram, you can draw from this concept. You have on the x-axis it is x, on the y-axis it is momentum p. Okay, for a harmonic oscillator, phase space diagram means a diagram spanned by the coordinate x and the momentum p. Okay, and when x increases from 0 towards right, from this concept you can see that its momentum will decrease. For x equal to 0, the potential energy is 0, so the kinetic energy will be some value. Then for that kinetic energy there will be a particular momentum. Let it be this value. Okay, for x equal to 0, let the momentum of the particle be this one. Now as x increases, the potential energy goes on increasing. That means kinetic energy will decrease. That is, momentum will decrease. But what is the direction of travel for momentum curve? It will be like this. Momentum will decrease. It will go like this. Okay. Now we have to fix some energy. Then only we can draw the phase space diagram. So let us take an energy value like this. Let this be the total energy of the harmonic oscillator. Okay, let this be the total energy of the harmonic oscillator. Then we can see that up to this point, let it be A, up to x equal to A, this potential energy curve is below the total energy value. Potential energy value is less than total energy up to x equal to A. That means kinetic energy will be positive. At x equal to A, total energy equal to potential energy. That means kinetic energy becomes 0 and momentum becomes 0. That is why this momentum reduces to 0 at x equal to A. And the direction of arrow is very important. The momentum decreases from a maximum value p. It is a positive value. Okay. Then it decreases and it reaches 0 at x equal to A. Up to that point, the particle is moving towards right. Particle is moving towards right means its position increases with the time. That means its velocity is positive. Position increases with the time means velocity is positive. That is why the momentum is positive. That is in the first quadrant. Okay, momentum is positive, x is positive. So x is increasing with the time towards right. So momentum is positive and its magnitude goes on decreasing as x increases. As x increases, kinetic energy will decrease because potential energy is increasing. Total energy is a constant, so kinetic energy should decrease. So momentum should decrease in magnitude and it will reach a 0 value at x equal to A. Then beyond x equal to A, no physical motion, because beyond x equal to A, potential energy is greater than total energy. Potential energy greater than total energy means E greater than half kx square implies negative kinetic energy. Negative kinetic energy means momentum should be imaginary. Okay, it's not possible. So no motion possible beyond x equal to A. So x equal to A is the extremum value. Now the particle will go back. Particle will go back. Up to this point it can move and its momentum will become 0 and then it turns back. It turns back. That is, now onwards x will decrease with the time. X will decrease with the time. That means its momentum will be negative. Its momentum will be negative. That is in the fourth quadrant. And as time increases, x is decreasing. X is decreasing, and for a for half of the period. Okay, when the time reaches half period, this particle will reach here. Again it is at the position x equal to 0. So it starts from x equal to 0 with some positive momentum. It will move on the right, and at x equal to 8 its momentum becomes 0 and it goes back. And when it reaches back to this origin, it will have a negative momentum. So it will cross this point and it will move on to the left, and it can again reach up to minus a. Then its kinetic energy again becomes 0, momentum becomes 0. So the portion can be represented on this side. During that journey, the momentum is negative because the particle is moving towards left. Its position x decreases with the time. Now, from this point, the particle goes back. Goes back means its x coordinate increases with the time. So it will be moving towards the right. Its momentum is positive and it goes on increasing up to x equal to 0. Its value goes on increasing, and the maximum value is at x equal to 0 because the minimum potential energy corresponds to maximum kinetic energy and maximum momentum. And beyond that point, its kinetic energy decreases. Again it reaches 0 at x equal to a. So the phase space trajectory will be something like this. It will be a closed curve bounded between x equal to a and minus a, and the momentum value is bounded between some p max. This is positive and this is negative. Okay, the positive negative concept is based on whether the x value is increases with the time or decreases with the time. Now, if I take the energy value something like say this, if this is the energy value, then the maximum value is minus b and plus b. The maximum possible value for x is plus b and minus b, because beyond that point potential energy is greater than total energy. This is the total energy. If you take a harmonic oscillator with less energy E2, okay, this is corresponding to energy E1. If you take a harmonic oscillator with a lower energy E2, then its phase space trajectory will be bounded between minus b and plus b. So it will be something like this. It will be something like this. Okay, again an ellipse, but its extremum point is minus b and plus b. Okay, this is for E2. So if you vary the energy, you can draw different closed orbits like this. Now, is it an ellipse? Is it an ellipse? We can check that by rearranging this equation. P square by 2m plus half kx square equal to E. You can rearrange that in this way: p square by root 2me the whole square plus x square by 2e by k root the whole square equal to 1. You can rearrange this equation p square by 2m plus half kx square equal to E as p square divided by root 2me the whole square plus x square divided by root 2e by k the whole square equal to 1. This is the standard form of equation of an ellipse: x square by a square plus y square by b square is equal to 1. So this is nothing but an ellipse. For harmonic oscillator, the phase space diagram will be concentric ellipses. I think it is clear. Now I will give you the plot of potential energy. Now I will plot the curve of potential and also the phase space diagram. Consider the case with the K is equal to 2, then potential energy V equal to half kx square becomes V equal to x square, and the curve of V equal to x square is shown in this red one. Okay, this red curve is V equal to x square. This is a parabola. Now let us fix energy E equal to 2. Okay, take an energy value E equal to 2, that is this point. Okay, this is total energy E. Then if you consider M as 1, then the equation P square by root 2me the whole square becomes P square by 2 whole square plus x square by root 2e by k the whole square becomes x square by root 2 square equal to 1. If we plot this, then we will get this blue curve, and you can see that the maximum value of x is this one. Okay, the maximum value that the variable x can take is this, and this is exactly equal to the value where the potential energy crosses the total energy. This is the limiting value for x. Up to this point, this potential energy curve is below the total energy, and beyond that point the potential energy is greater than total energy. That is not physically possible. Okay, now if we reduce the energy to E equal to 1, then you will get this ellipse, and you can see that for the second case, total energy E equal to 1, that is this value, the x value is restricted to this point. Okay, where this total energy crosses the potential energy curve. So I think the idea is clear. This is the phase space. The potential energy curve is shown in this red color, and the phase space diagrams for two energies. For E equal to 2, this is the blue curve. For E equal to 1, that is this yellow curve. Okay, this is the phase space diagram of harmonic oscillator. Now, if you change the potential to something like V of x is equal to k into mod x. What is the meaning of k into mod x? Its value is minus kx if x less than 0, and its value is kx if x greater than 0. And the plot of such a potential is like this. The plot of such a potential will be like this. This is the plot of potential. Okay, mod x, V of x versus x. Okay, now the Hamiltonian, you can write it as p square by 2m. This is a single particle moving in a one-dimensional potential like k mod x. Then Hamiltonian becomes p square by 2m plus k mod x, and that is nothing but total energy. Again, it's a conservative system. Total energy. Now you can write it as P divided by root 2me the whole square plus mod x divided by root e by k is equal to 1. But it is not the expression of an ellipse. But we can draw the phase space diagram by the similar arguments that we took in the earlier case. That is, you consider a total energy. Okay, you have to fix the total energy, then only you can draw the phase space diagram. Let the total energy be this value. Okay, let the total energy be this value. Then from the same arguments as we did before, let us start from x equal to 0. Its potential energy is 0. Potential energy 0 means it will have some momentum. Okay, so let that momentum be this value. Then as x value increases, its potential energy is increasing linearly. Okay, linearly. That means its kinetic energy will decrease linearly, and hence your momentum will also decrease, but it is not linearly. Okay, it's square, p square decreases linearly. Okay, so p will decrease something like this. It is not in the form of an elliptical curve. Okay, it is something like this. Then it will reach up to this point A. Okay, up to this point. Beyond x equal to A, this potential energy will cross the total energy. That is, kinetic energy becomes negative. That is not possible. So the particle can go up to x equal to A. Then its momentum becomes 0, and then the particle will come back. Okay, then the particle will come back. Particle will come back. Okay, now when it reaches x equal to 0, as it comes back, its x value is decreasing, so the momentum will be negative, and its value becomes maximum when it reaches at x equal to 0. Then it crosses the point and it goes to the negative side again with a negative momentum. So it will be something like this, and then it will go like this to this point. So the curve will be something like this. Okay, it is not of the form of an ellipse. It will be a bounded curve, but it will be something like this. It is not an ellipse, but it is a closed curve, something like this. The arrow diagrams, the arrows should be like this. As x increases, momentum, a positive momentum will decrease to 0, and then as x decreases, the negative momentum increasing up to this point, then it's decreasing up to this point, and then like this. If you take another value for energy, something like this, if you take another value for energy, then the phase space diagram will be something like this. Okay. Now I will plot this for some values of k, e and m. Again, let's take k is equal to 2, m is equal to 1, e is equal to 2. Then that equation becomes p square by 4 root 2me whole square, that is 2me, p square by 4 plus mod x divided by it is root e by k, that is 1 equal to 1. Okay, so let us plot that curve. Functions. It is not a Cartesian function, it is an implicit function. P square. Vertical axis it is y. So y square divided by 4 plus absolute value of x divided by 1 equal to 1. Okay, it will be like this. It will be something like this. I will plot the potential energy curve also. It is Cartesian. It is k mod x. K is 2, so it is 2 into absolute value of x. I think we can take y from -3 to 3. Okay, it will be something like this. So it is not an ellipse. It is not an ellipse, but it is not a. But it is a closed curve. It is a closed curve. The bound is at this point. Okay, the maximum value of this is the total energy is. We are taking it as 2. In this example, I took total energy as 2. So the maximum value for x is up to this value, where the total energy and the potential energy crosses over. Okay, up to this point the particle can move, then it will go back. Okay, I think it is clear. If I decrease the energy value, if I take E as 1, then this becomes p square by E is equal to 1. So root 2 me becomes p square by 2 plus mod x divided by E is equal to 1. So it is 1 by 2 the whole square equal to 1, right? Here I forgot to put a square, root E by k square. Okay, then here E is 1k, so root 1 by 2 square is, this is not okay. So if I plot that, it will be something like this. The denominator of y square is 2 and the denominator of this is 0.5. That happens absolute value of x. Implicit y square divided by 2 plus absolute value of x divided by 0.5 equal to 1. Okay, it will be like this. Okay, so this is the phase space trajectory of v of x equal to k mod x. Now I will consider another example. V of x is equal to minus half kx square. Then h is equal to p square by 2m minus half k x square is equal to total energy. Okay, or we can write it as p divided by root 2me the whole square minus x p square divided by minus x square divided by root 2e by k the whole square equal to 1. So it is a hyperbola. So we can analyze this like this. First you have to plot the potential energy as a function of x. Here it is minus half kx square, so it is an inverted parabola. The first example we considered a parabola, but now it is an inverted parabola. Something like this. It is an inverted parabola. this is minus half k x square. This graph is minus half k x square. Now the phase space diagram, how it looks like. We consider a graph with position x on horizontal axis and momentum p on vertical axis, and this is 0. Here you have this is 0, and you have to fix an energy value. You have to fix an energy value. Let it be this one. Consider an energy value like this. This is total energy. This is total energy. Now suppose you start from some negative value of x, say from here, okay, x is equal to say minus a or something, okay, you started from here, and as x increases with the time, its kinetic energy at this point, its kinetic energy is let me start from this point. Then its kinetic energy will be this difference, okay, this difference, because the difference between total energy and potential energy, total energy and potential energy will give you kinetic energy. So at this negative x value, the particle has some kinetic energy, so it will have a momentum. At this point, okay, it will have a momentum. It's a positive momentum like this. It's a positive momentum. Then as x increases in this direction, the kinetic energy goes on decreasing. The height between the total energy curve and potential energy curve goes on decreasing. This difference is decreasing up to this point. At this point, the difference becomes 0. That is, kinetic energy becomes 0, momentum becomes 0. So this momentum started from this value, it will go like this, decreasing and become 0. Okay, this momentum decreases to 0 at this point. Then this particle can never go beyond this negative x value, because the total energy is less than potential energy up to this beyond this point. Total energy is less than potential energy, means kinetic energy becomes negative. So this particle will go back like this. So the particle will come from a negative x value and it can reach only up to this point, then it will go back. Okay, here this will be something like this. So it will come from this point, arrow like this, and it will go towards this point. Now if the particle started from a positive x value somewhere here, again if the x value decreases with the time, its kinetic energy, the difference between the red curve and black curve, is decreasing up to this point. So the momentum, it is moving in the negative x direction. So the initial momentum is negative. So at this point, the negative momentum, then its momentum decreases to 0 at this point, then it will go back. Go back means its momentum is positive. It will be moving in the positive x direction. So the trajectory will be something like this. So it is a hyperbola. Okay. If you take another energy like this, if the energy is this, then particle can reach up to this point. So the curve will be particle can reach up to this point. Okay, so the phase space trajectory will be like this. The arrow, direction of arrow is very important. Okay, it will be like this. Now, if the energy is something like this, a positive energy is something like this, then what happens? Then the particle will start from somewhere here. Then as it moves or in the positive x direction, its momentum will get decreased because the difference, the total energy and potential energy difference goes on decreasing. But even at x equal to 0, there is some momentum, positive momentum. So the particle will go to the other side. Okay, if your energy is like this red curve or this green curve, the particle can never go beyond this x equal to 0. Okay, it can reach only up to some point and it will go back. Okay, it is not possible to climb up the hill. If you can consider this as a hill, this particle with the red energy, it can go only up to this point. This green one can go up to this point. Okay, if energy is little more higher, it can go up to some more height. But if you have a positive energy, you can climb up the hill and go to the other side. So the diagram will be something like this. It will go to the other side. It will come from here, it will go to the other side. And if the particle is starting from this side with the positive energy, it will go to this side. Okay, so that trajectory will be something like this. So depending on the initial condition, you can draw this on top side or on the bottom, but you have to be careful about the arrow, direction of arrow. Okay, if you are moving towards left, x is decreasing with the time, so the initial momentum is negative. So that is why it is in the negative y direction. Now there is a special case. What about the total energy equal to 0? If the total energy is 0, what happens? If E equal to 0, that is the yellow curve, what happens? The particle, if it starts from a negative x value, it will climb up the hill, climb up. Its kinetic energy decreasing, so its velocity is decreasing. And when it almost reaches the top, velocity will almost have 0 value. Since the velocity is very low, it will take a long time to reach the top of the hill. And theoretically, it will take infinite time to reach x equal to 0. Or practically, it is not possible to reach x equal to 0. If a particle has 0 energy, then as it moves in this direction from this point, say x equal to a large negative value to x equal to 0, its kinetic energy goes on decreasing, its velocity goes on decreasing, and it approaches very close to 0. Its velocity is very small, and it will take infinite time to reach x equal to 0. So the curve will be something like this. It will come from here and it approaches x equal to 0 with a very small velocity. It will almost take infinite time to reach x equal to 0. Okay, and why it is a straight line? Because when x equal to 0, p square by 2m equal to half k x square, or p square is equal to p square equal to mk x square, or p is equal to plus or minus root mk into x. So it is a linear curve. Okay, now I am plotting p equal to minus root mk x, and this direction is like this. Now if the particle started from this side, it will be something like this. Okay, the arrow will be like this. Suppose somehow the particle reaches the point x equal to 0. Okay, it will take infinite time actually, but somehow if it reaches x equal to 0, that is actually an equilibrium point. It is the top of a hill. The potential energy is maximum. That is dV by dx is 0. That is force is 0. Okay, force is 0. Force 0 means that particle is at equilibrium. The particle will stay there forever if there is no disturbance. But if there is some perturbation or some disturbance, it will move from there and it will never come back. It will never come back because it is a maxima. If it moves towards right or towards left, its potential energy goes on decreasing. That means its kinetic energy will goes on increasing. It will never come back. Its velocity will increases and increases. So it will never come back. So this point x equal to 0 is actually an unstable equilibrium. If you place the particle exactly at x equal to 0, it will stay there forever. If there is some perturbation, it can move to infinity either towards left or towards right. So this point itself, this point x equal to 0 itself is an equilibrium point, and that is an unstable equilibrium. That is an unstable equilibrium. If you give some perturbation, the particle will go to infinity either towards this direction or towards this direction. These four lines which separates the two sets of curves, one parabola, hyperbolas like this, that is negative energy curves, and one the positive energy curves, hyperbolas like this. Okay, the yellow curve separates these two sets of curves, and these are known as separatrix. These are known as separatrix. Separatrix. Okay, these are the limiting case, e equal to 0. Okay, so these are actually the asymptotes of hyperbola. Asymptotes of hyperbola. But you have to take care of these arrow directions. Arrow direction. At all points the arrows are consistent. All is in this direction. Here all are going to infinity. Here also all going to infinity. Here all are pointing towards origin. So this is the phase space diagram of V of x equal to minus half kx square. So whenever you have a hill like this for the potential energy, the phase space diagram will be like this. Whenever you have a dip like this, your phase space diagrams will be closed on. Okay, about that bottom of the this curve. Okay, about the bottom of curve you will get concentric ellipses if you are like half kx square parabola. If it is a minus half kx square parabola, it will be hyperbolas like this. Okay. Now let me plot these curves. V of x is equal to, let me take k equal to 2, m equal to 1, e equal to 2. Then V of x is equal to minus x square. And the other equation is p square divided by root 2me. Root 2me. So p square by 4. Root 2me whole square. So p square by 4 minus x square divided by root 2e by k equal to 1. Okay, so let me plot this graph. First we will plot f of x is equal to minus x square. The graph will be like this. Then we will plot implicit curve y square by 4 minus x square by 2 equal to 1. Then we will plot for some negative energy. negative energy. I will first evaluate what is its value. Suppose E equal to -1. Equal to -1. Then this becomes P square divided by root 2me the whole square. P square divided by equal to -1 -2 minus x square divided by -1 equal to 1, right? So this becomes minus p square divided by 2 plus x square divided by 1. Okay, it will be like this. I'll change the color. Now what happens if energy is equal to 0? If energy is equal to 0, then it will be, the equation is p square by 2m minus half kx square equal to 0. So p square by 2m, m is 1, p square by 2 minus half kx square minus x square equal to 0. Okay. Take the color as these are the curves. Okay, this yellow one is for some positive energy. This green one is for negative energy, and this one is for zero energy. This is the shape of potential. Okay, I hope it is clear. So this is the way which we can draw phase space diagrams. I will give you one more example. V of x is equal to some x square minus x raised to 4. Suppose the potential is like this: V of x equal to x square minus x raised to 4. Then the process of plotting the phase space diagram is very simple. P square by 2m plus this value x square minus x raised to 4 is equal to E. Okay, total energy. So depending on the value of total energy, we will get different curves. First we can plot this potential energy curve. That is potential energy in this case. F of x is equal to x square minus x to the power 4. This is the potential energy. Potential energy okay. This is the potential energy curve. So here you have two maxima and a minima. Okay, so around the minima you will have concentric ellipses, and around maxima, not concentric ellipses but concentric closed curves. Okay, it is not always ellipses. It will be all ellipse only if it is an x square or quadratic minima. Okay, so in any minima you will get closed curves, and for about any maxima you will get unbounded trajectories. So for about any minima you will get bound trajectories, about any maxima you will get unbounded trajectories. So there are two maxima and one minima. Okay, now we'll look at the phase space diagram. This is E. So if I write the equation, that will be something like p square by 2me plus x square minus x raised to 4 divided by e is equal to 1. Okay, let me take m is equal to 1 and e is equal to, say, 2. Okay, take an e equal to 2. Then the graph will be something like, you have to take implicit function plot, then p here is y square divided by 2me becomes 4 plus x square minus x to the power 4 divided by e is 2 equal to 1.